differentiation is one of those things that's going to show up at different times and at different parts in this class. It's like in this unit, we're just going to focus on like, can we find a derivative implicitly? The next unit, we'll actually look at some calculus word problems that will require implicit differentiation, and then it shows up again frequently in second semester as well. So what do I mean by implicit differentiation? Before I get to the calculus, I think it's nice to just talk about what do I mean by an implicit function. An implicit function, the way I think about it, is it's going to be an equation, and I should be more clear, I shouldn't say implicit function, but a graph defined implicitly is basically mixing up together the x's and the y's on the same side of the equal sign. That's going to be compared to what we say is an explicit function, where an explicit function is in the form of y equals, and then x on the other side. Some equations, if it's written implicitly, it's pretty easy to change it and write it explicitly. For example, if I have y minus the tangent of x equals 0, that would be implicit because we have a mixture of x's and y's on the same side of the equation. The explicit version of this equation would be y is equal to the tangent of x. Similarly, in that second row, I have y cubed plus 2x is equal to 5. That would be an example of an implicit function. An explicit function would be the cubed root of 5 minus 2x. I wouldn't need the plus or minus there because that is an odd root. X times y is equal to 8. That's an example of an implicit function. An explicit function would be y equals 8 over x. And often when you're asked to find the derivative, if you have an implicit function and it's easy to solve for y, that is what you want to do because it's going to be easier to take the derivative when it's y equals and then x on the other side. This last example is one that you would have to take the derivative implicitly because there's no easy way to solve for y. Say it again. So that last one we do have, that last one would be one that we would leave implicitly because we have a mixture of x's and y's and we can't easily solve for the y. So when we're taking the derivative, to kind of start off on the baby examples, I just want to kind of look at examples where this thing called implicit differentiation is needed. So the notation I'm going to use for implicit differentiation, I do tend to use the likeness notation, the dy dx, instead of like the y prime or the f prime. If I see d dx, I have not mentioned it a lot recently, but that dx in the denominator means you're taking the derivative with respect to x. For all the problems we've done so far, that has kind of just been understood. Like if I say take the derivative of the sine of x, like it's been understood we're taking the derivative with respect to x. Since we're taking the derivative with respect to x and the variable we see is an x, there is no issue. We don't have to do implicit differentiation. We know that the derivative of x squared is 2x. Likewise, we don't often see this, but I can take the derivative with respect to y. So if I say take the derivative with respect to y of y squared, those variables match, and I can easily take the derivative, and that would be 2y. Where implicit differentiation is going to come into play is when the variable that you're taking the derivative with respect to, I'm going to use WRT for that. So we're doing it with respect to x, but the variable I have is a y. Those are going to be the problems that are going to require you to do implicit differentiation. I'm going to tell you the answer to this one. I'll explain kind of the theory behind why it is the way it is. The derivative of y squared itself is 2y, but we're taking the derivative with respect to x. So how we kind of think about this is y is usually equal to something. Y is a function itself defined in terms of x. So we kind of have to do a chain rule here. The derivative of y squared is 2y, but we have this chain rule going on where the derivative of y is dy dx. So in order to fix that problem, as an implicit example, we're going to multiply it by dy dx, where dy is the variable that you have, and the dx is the variable that you wanted, is kind of how I think about it. We wanted to take this derivative with respect to x, but we were stuck with just the y variable, so we have to multiply it by this like fixer piece. And it is directly related to the chain rule. So look at some other baby examples before we get to like the AP level version. Implicit differentiation is really an application of the chain rule. You've technically done implicit differentiation, we just haven't written the step fully because it hasn't been necessary. So for example, this is the one that we just did. It was d dx of y squared. The variable at the bottom did not match the variable you're taking the derivative of, so you had to say the derivative of y squared is 2y, and then fix it with y dx after it. This second example, I have d dy of y squared. These match, so you would not have to use implicit differentiation. We know that the derivative of y squared would be 2y. We saw that on the previous slide. Technically what's happening still here though is you're multiplying by the derivative of y with the chain rule, but we had a y and we wanted a y, so when you multiply it by dy over dy, that's just the same thing as a 1, so that's why it's not necessary. I haven't showed you that because it hasn't been necessary when we take the derivative. You can take the derivative with respect to any variable. A common variable I often see us taking the derivative with respect to is t. T often for like time, so you can say what's the derivative with respect to time. So this is d dt of y squared. The variables don't match. The derivative of y squared is 2y. Then we have the fixer piece. We had a y, but we wanted a t. So the short answer for implicit differentiation is when you're taking the derivative with respect to a variable, if the variable you have does not match that variable, you're going to have to multiply it by this derivative kind of fixer piece. To look at more of a calculus example and kind of see where we're headed with this. This first example, I wanted to choose one where we do not need to have implicit differentiation. We have y is equal to 3x squared. And we know, like I said, hey, find the derivative of that. And you know that the derivative of that is simply 6x. Power rule, 3 comes down in front, and we have 6x. What was really happening in that, so we jumped from that statement to that answer. What's really happening is this is still an equation. This is y is equal to 3x squared. And we know for equations we have to take the derivative, or excuse me, what we do to one side of the equation we have to do to the other. So when I take the derivative, I'm literally taking the derivative on both sides of my equation. And again, we didn't show this because it wasn't really necessary for this problem, but I think it's a nice way to kind of ease into showing you why implicit differentiation is necessary. Looking on the right-hand side, I'll do that one first. The derivative of 3x squared, those variables match, and that's going to give us the 6x we know is true. Technically, we have implicit differentiation here because we had an x, and that is what we wanted. On the left-hand side, we do the derivative of y. The derivative of y is 1, but we had a y, and we wanted an x. Well, d dx, that's just going to give you a 1, and that's where the 6x is coming from. Well, 1 times dy dx, what's another way of writing dy dx? Writing dy dx is the same thing as saying y prime. So you have technically in some ways been doing implicit, you just didn't realize it because we were just jumping straight to the answer without showing all those middle steps because they're not necessary. Where they are a little bit more necessary would be an example like this. I have the sine of y is equal to 3x squared, which is actually going to graph a type of elliptical shape. And if I want to find the derivative of this graph, so it's not a function, but of this curve, this graph, we do want to take the derivative of each side. The derivative of sine of y, we're doing it with respect to x. Of sine is cosine of y. Since that y was not in terms of x, we have to multiply it by the fixer piece. So we're going to multiply it by dy dx. And then on the right-hand side, the derivative of 3x squared is 6x. We don't need to do implicit differentiation because we took the derivative with respect to x, and it was already in terms of x. That is the derivative. Oftentimes we'll like clean it up by solving for dy dx. So you can say something like if you divide by the cosine of y, dy dx is equal to 6x over the cosine of y, or that's the same thing as saying 6x times the secant of y. What's unique about the derivative of implicit graphs, implicitly defined graphs, is that often you'll see, like in this case, the derivative doesn't only rely on the x-coordinate, but it relies on the x and the y-coordinate. So it has a little bit of a more complicated derivative. Let's look at another example, and then I'll take some questions. So here's that same function, but now we're going to take the derivative with respect to t. I kind of removed the context from it, but we could talk about maybe like a particle is moving around the graph, and we want to find like at the rate it's moving around at. So we're taking the derivative with respect to t. Again, since it's t, the x and y do not match what you're taking the derivative of, so you have to do implicit. The derivative of sine is cosine. Multiplying it by the fixer piece is equal to the derivative of 3x squared, which is 6x times the fixer piece. Notice when I took the derivative of something with y, it was multiplied by dy dt. When I took the derivative of something with x in it, we multiplied it by dx dt. Those two values would be different because one is basically the rate of change of y with respect to time. The other one is the rate of change of x with respect to time. Any questions so far about implicit differentiation? Yes, Zach? Like you can rearrange it, but not really. Unless it said like solve for dy dt or solve for dx dt, there's not really a nice way to simplify that one.
So you never separate the dy dt?
Usually at this point you have something to plug into it and solve for a missing variable.
The dt's cancel?
No, so we have to think of this as like, this is a single statement. The question for those of you at home was like, could you multiply by dt to basically cancel them out? But remember, we have to think of this as like a derivative, so that whole statement is like one symbol that goes together. Yes. In this case, like next semester we'll learn cases where we can break it apart, but right now, no, we can't. So go ahead and try these two for me. There's actually three, but I'm going to show two right now. Any derivative rule we have learned or any derivative rule we will learn, you can do implicit differentiation on. So don't forget about the chain rule, the product rule, or the quotient rule. But go ahead and try these two for me. Don't worry about solving for anything. I just want you to take the derivative of both sides with respect to x. And then I have a third one I'll scroll down that we'll look at that I think is a little bit trickier. So this first one, similar to other derivative rules, you just take the derivative of each term. The derivative of sine of x with respect to x is just the cosine of x times dx, but the cosine of x. The derivative of sine of y with respect to x is going to become the cosine of y and then the fixer piece, dy dx, is equal to the derivative of y squared with respect to x is 2y times dy. We could solve this one for dy dx, but I just want to worry about the actual derivative part right now. This second one is a little bit more complicated. This is the sine of x times the sine of y. So you are going to have to make sure we use the product rule for this one. So using the product rule, I have the first times the derivative of, there's my implicit differentiation, plus the second times the derivative of the first, and then on the other side we have the 2y dy dx. Notice when you do implicit differentiation, you only multiply by that dy dx when you took the derivative of y, and it happens immediately after you took the derivative of y, just like the chain rule would work. And then I have this last one. Looking at this last one, this is the sine of x times y. I think this one's the trickiest one because we do have to worry about the chain rule. And then inside the chain rule, we have a product because this is the sine of x times y. So using the chain rule, the derivative of sine is cosine. The inside stays the same. And then we have the chain rule. The derivative of the inside, I have the first times the derivative of the second. The derivative of y is 1, and then we have dy dx. Plus the second times the derivative of the first, and then we have equals 2y dy dx. Again, you can simplify those. Usually these problems have a lot of algebra in them. But does anyone have any questions on those three problems? All right. So when we're looking at these problems, anything that we can do with the derivative, you can also do with a function that's been implicitly defined. So you can find tangent lines, you can find minimums and maximums, you can find intervals of increasing and decreasing, concavity, anything with a derivative, again, because this is just another way of finding a derivative for certain types of graphs. To start off, I want to do like a really basic one of just finding a tangent line. And so I have this curve right here. The curve is, I have y cubed plus 2 is equal to x minus the sine of y. So your graphing calculators can't graph implicitly defined functions, but a program like Desmos can graph them pretty easily. So looking at the questions I have, I want to first differentiate both sides with respect to x. And then the second question is I want to find dy dx in terms of x and y. I want to kind of talk about the differences between those questions. If it just says to differentiate with respect to x, that part's just asking you to take the derivative and then stop. So if you see that as a question, take the derivative and then stop. But if you see a question that says find dy dx in terms of x and y, that one is going to ask you to take it a little bit further. Not only do you need to find the derivative, but you need to solve for dy dx. And then the last question is going to deal with a tangent line when we get there. So let's go ahead and find the derivative. Again, we're doing this with respect to x. So if I'm just taking the derivative, that's going to become 3y squared dy dx. The 2 is going to go to 0, so the derivative of a constant, is equal to the derivative of x is 1 minus the derivative of sine is cosine, and then we have the fixer piece of dy dx. So that's the derivative. The second question, though, wants us to find it in terms of dy dx, which is a very common thing the AP exam asks you to do, especially on like a multiple choice question that wants you to get it into the same form. To get it into dy dx solved by itself, the algebra is pretty much straightforward. You get like any term with a dy dx on one side, anything without a dy dx on the other side of your equal sign, factor out the dy dx, and then divide by what's left over. So if I'm looking at this problem, I have two terms with dy dx attached to them. So I can go ahead and subtract. I'm going to subtract the cosine one to the other, really add it to the other side. And so I've separated dy dx is on one side, everything else on the other. Since both those terms now have a dy dx in them, I factor it out. And then if I'm solving for dy dx, I just want to divide by what's left over. So we can see that the derivative dy dx is 1 over 3y squared plus the cosine of y. This is a pretty interesting derivative because it doesn't rely on the x-coordinate at all. It just relies on the y-coordinates. Any questions on the first two parts of that question? All right, so now let's do the tangent line. This is just review at this point. To find a tangent line, we know we always need two things. We have to have a point, which they gave us, and we have to have a slope. We know the slope is going to come from the derivative. My derivative is dy dx. Instead of just plugging x into it, I'm plugging in the entire coordinate, which in this one it only has a y. Plugging in that y coordinate, the cosine of 0 is 1, so we have 1 over 1. So my tangent line, y minus the y coordinate, is equal to the slope times x minus the x coordinate. And that is the equation of the line tangent to the graph at 2, 0. Questions on that? So again, anything you can do with the derivative can apply with implicit differentiation. I don't have all the types of examples that we can see in the notes today, but there are a few I want to look at. To show you the graph of this, like you don't have to know what the graph looks like, but I did go ahead and graph it for you. That blue one is the original graph. I keep saying function, but it's not necessarily a function. But this one is a function, I do believe. I don't think it repeats on itself. But the blue one's the graph, and then you can see what we found in red is the tangent line. The next thing I want to look at, often we want to be able to analyze certain types of graphs with these problems. So I'm going to save this problem as a warm-up for tomorrow, and I'm going to skip and jump to this problem, if you're following along in OneNote. So oftentimes, since these graphs are not ones that we're often familiar with, we want to be able to analyze key parts of the graph. And the key parts we often want to figure out is where's this graph going to have a horizontal tangent, and then also where are these graphs going to have vertical tangents. We know that horizontal tangents show up when the derivative is equal to 0. When the derivative is equal to 0, a lot of these derivatives we're going to find implicitly are going to end up being like a fraction. So if we're setting the whole derivative equal to 0, often we're just setting the numerator equal to 0 because the denominator is going to cancel out. And then we also want to find vertical tangents. These graphs often have loops in them, or they're elliptical, and they have lots of curves to them. So we often want to find vertical tangents. We know vertical tangents are when the derivative is undefined, because the slope of a vertical line. Where are derivatives usually undefined? Derivatives are usually undefined when the denominator is equal to 0, because we know we can't divide by 0 in mathematics. Go ahead for me, just for practice, go ahead and find the derivative of this with respect to x, and then solve for dy dx. So go ahead and find the derivative, and then solve for dy dx. And we're going to take the derivative with respect to x. At my work, taking the derivative of y squared is 2y multiplied by the fixed piece dy dx plus the derivative of 4y is 4 times dy dx equals, we can do the derivative of 4x cubed usually, so just 12x squared. If I'm solving for dy dx, this one's nice because the two dy dx's are already on the same side of the equal sign, so I can just factor it out and then divide by what's left over. So I end up with that the derivative of this graph ends up being 12x squared over 2y plus 4. And so we want to look at where we have horizontal tangent lines and vertical tangent lines. Those are going to occur again. We have horizontal tangent lines when the derivative is equal to 0, which is going to show up when the numerator is equal to 0. So that's going to be when x is equal to 0. This derivative is undefined when its denominator is equal to 0, or when y is equal to, subtract by 4 divided by 2 at negative 2. Do be careful here, that doesn't mean there's like this coordinate of 0, negative 2. Those are like two separate places on the graph. The original question, I did ask us to find the x and y coordinates because some things can happen when you have these implicitly defined functions. In that, again, I keep saying it, they're not always functions. Sometimes you have more than one y for each x and things like that. So we know that we have some horizontal tangents when x is equal to 0. If I want to figure out where those are exactly, similar how you would treat any other graph, if I have the x coordinate, to find the y coordinates that go with it, I can just plug it into the original function. So plugging that back into the original function, we have y squared plus 4y is equal to 4 times 0 cubed. So that's just y squared plus 4y is equal to 0. That is a quadratic. It's already equal to 0, which is nice because we know to solve quadratics, it has to be equal to 0. Factoring out a y, we have y times y plus 4 is 0. So I get y is equal to 0 and y is equal to negative 4. What does that mean? That actually means that there's two coordinates where we have horizontal tangent lines. We have one coordinate when x is 0, y is 1. That is a horizontal tangent line. We also have another horizontal tangent line when x is 0 still, but when y is negative 4. So this graph actually has two horizontal tangents, both when x is equal to 0. And then I can do a similar thing for the y. For vertical lines, we saw that there is a vertical tangent line when y is equal to 2. So I can go ahead and plug in, negative 2. And use that to solve for x this time. So I have 4 minus 8 is equal to 4x squared. Did I mess up somewhere? Cubed, thanks. 4x cubed. So x cubed is equal to negative 1, x is equal to negative 1. So what does that mean? It means that when y is negative 2, x is negative 1, and that's where we end up having a vertical tangent line. So there's kind of three key points on this graph. Two where we have horizontal lines, and one where we have a vertical one. Any questions on that work?
Does the y coordinate really matter for the vertical tangent line? Like, I know we used it to find it, but do we really
so where it's useful, so the question was asked, is that y needed? And I think it's needed because when you look at the graph, it gives you an idea of what the graph looks like. So I've kind of already did the calculator to see it, but we can see kind of clearly that we do have horizontal tangents at 0, 0, and 0, negative 4. And now we know visually that at negative 1, negative 2 is when the graph ends up being vertical. So it can give you an idea as we start finding other bits and pieces of this graph, like what is the graph going to ultimately look like if we didn't have technology in front of us to find like when is it vertical and when is it horizontal.
So it's more when the graph itself is vertical, not when there's like a vertical line that's just stopping the graph.
Correct. So it's just going to be at one point where we have a vertical tangent. The next problem takes too long to do for me to do in 10 minutes, so I am going to stop there for today. Tomorrow we'll do a warm-up. We'll find this tangent and line just for practice, and then we'll talk about second derivatives and implicit differentiation. Your homework tonight is going to be implicit differentiation. It is in the textbook. Please skip, so I have 4 through 40 multiples of 4, but please skip number 20. You are not required to know the problem and like the math used for number 20. Same thing, 46 through 58 evens, but skip 56 because you are not required to know how to do 56. Tomorrow we'll finish up these notes, and there will be some AP problems assigned for you to practice with. And then next week you have a long weekend. Wednesday and Thursday are going to be straight review days, and this is a quick unit. We'll be testing on Unit 3 on Friday of next week. And then the unit after this, creatively more applications of derivatives. So at that point, if you're at home, I will let you go now, and we'll finish these notes tomorrow. Feel free to hang back if you wanted to ask any questions, and we'll finish these notes up tomorrow.